Yeah, I introduce myself. I'm a colleague of Antonio, so this work comes from the same institute, that is STEMS, is one research institute from the National Research Council in Italy. And today I'm going to present an update of our work on the development of highly performing dual function materials based on ruthenium for the integrated CO2 capture and methanation. And I will briefly repeat some of the concept of the background. That is, we all know that we need a strong reduction of source greenhouse gases emissions to become carbon neutral. And one of the main challenges is to sustainably convert CO2 emissions from industrial processes or even CO2 from air into synthetic fuels that are also known as e-fuels. And this approach is often named as power to X. And these e-fuels, synthetic fuels, are really fundamental for the decarbonization of hard-to-abate sectors. Because we do not have so many alternative options. So the idea is that we capture CO2 from point sources or even from air. We can react it with hydrogen from renewable sources to obtain a carbon neutral cycle or even a carbon negative cycle. And this is also a way to store the excess of renewable energy. And among the many fuels that can be considered, methane is advantageous for short-term application because there is an existing distribution grid, and it can be easily handled and also easily utilized. So basically the technology, CCU technology, is already available at the moment, but what we have right now is let's say multi-step processes that include many energy intensive steps, specifically the sorbent regeneration for CO2 capture takes a lot of energy, and also you need to compress, transport, and purify your CO2 before it can be reacted. So a few years ago, the idea came out to integrate the two processes of CO2 capture and conversion into a single process that is highly efficient, and is a chemical looping process. And is mediated by the presence of what is named dual function material. And in this way, it is possible to avoid the regeneration of the sorbent and the compression, transportation, purification of the CO2. And this is actually a platform, a technological platform, because you can use this approach to obtain many alternative products by simply changing what is the reaction condition and the hydrogen source. So you can use hydrogen to obtain methane and syngas, but you can also produce olefins, or you can even think to go to methanol, just to mention a few of the possibilities. So if we now focus on the capture and methanation, the process is indeed composed of split in two half steps. The first part is the adsorption. So you have a material that is capable to absorb CO2 from a flue gas, for example. And when exposed to this flue gas, the sorbent phase in our dual function material tends to saturate with CO2. And then when this is completed, we just switch the atmosphere where we expose the dual function material, and the CO2 is now exposed to an hydrogen gas containing gas, for example, and CO2 that was previously captured is desorbed or spillovers onto the active sites for the hydrogenation to methane. Obviously, the two steps are repeated cyclically, and this can be done in basically two configurations. One is with two fixed bed reactors. that entail alternate feeds and also require an intermediate purge to avoid the contact between, let's say, the oxygen in the air or in the flue gas and the hydrogen in the process gas. And it can be theoretically run under isothermal operation, and it is difficult to change the temperature of the two reactors, obviously. But we will see also that both steps are not are exothermic, so with fixed bed reactors we could have some problems in the heat removal. The other possibility is to have two reactors that are interconnected and to circulate the dual function material in between the two reactors. And they can be fluidized bed reactors. And really, a few weeks ago, I found the first publication with on moving bed reactors. And the further advantage in this case is that we can optimize individually each of the two reactors, and we can also have better heat transfer, for example, with fluidized bed reactors. But then there are many other problems that arise due to the mechanical stability that is required to our dual function material for the problems that are connected to the attrition or fragmentation, for example. So the key to success in this integrated process is actually the dual function material. And we have to carefully match the adsorption and the catalytic feature, and they have to be matched in the same temperature range. So for CO2 adsorption, we want a large CO2 capacity. We want the sorbent phase to be selective for CO2 in real exhaust gases or even in air. We want fast adsorption kinetics, and the absorption phase has to be easily regenerated. And we also want, and I want to stress this point, to have minimal parasitic H2 consumption. So we should try to avoid sorbent phases that can be easily undergo redox cycles, because that would entail a parasitic consumption of hydrogen, and the cost of this process is really the green hydrogen that we need to power up the process. On the side of the activity, the methanation activity, obviously we want high activity at the same temperature, and we want catalyst that is selective for methane formation. We want to have a complete, in this case, redox cycle of the active phase, because generally for the methanation, the activation of the methanation reaction, we need a metal active site. The system has to be durable upon this redox cycling, and we would like to have a tolerance to poisons, and also to keep the cost affordable, because if we have precious metals, obviously we have to keep it the loading of the precious metals as low as possible. So it is a matter of balance, and in our lab we have tested several systems, and basically our focus is on ruthenium catalyst, ruthenium methanation catalyst, that is ruthenium dispersed on gamma alumina spheres, and this is the active site. These are the active sites for the methanation. And for the storage material, we used to dope the system with lithium or sodium. And sodium is possibly in the open literature the most studied element for the low temperature methanation. But we have found that with lithium we can obtain good performance in terms of capture capacity, but definitely a faster methanation rate. So if you compare these results here, this is CO2 capture at room temperature, and you can see in this phase, and but with the same amount of alkali metal, we capture more CO2 with sodium than with lithium. Then we switch to hydrogen and we ramp up the temperature and we start forming methane. And you can see that with lithium we obtain the peak formation of methane at much lower temperature than with